All right, this is the last lecture and also the last of the series, Statistical Process Control. Okay, so before we move on, let's quickly review what we had covered last week before the break. Okay, so last week we had covered attribute control charts. Technically speaking, we have P chart, NP chart, C chart, U chart. Okay, each of those charts try to work with one case. Either it can be to classify some event as confirming or non-confirming, good or not good, go or no go, or uh, they will work to count the frequency of some events. For example, the the number of time uh, the number of time that we have some kind of accidents in a week in a city or something like that. So usually it will be tied to a fixed or even variable opportunity size, a constant or even variable size of opportunity. However, those have serious limitation, and we already know if the average number of counts less than 20 is actually problematic because some of the band will be very narrow, and that is why in this lecture uh, the new type of control chart will try to overcome all those issues. So that is why we have variable control charts. So what does it mean, variable control charts? So as you already familiar with the term variable, basically we will measure something. So this means these are always quantifiable. It doesn't just mean we count something, but something will have measurable unit. So variables data usually consist of things such as like weight, length, width, volume, okay, volume or size, not just length, but width, size, the height and something. So all these are measurable. And since these data are actually measurable, this means they have more information than the attribute data. Remember the attribute data only we have a very vague or mostly qualitative parameters. So as you can see, because of the data, the nature of the data already have more information embedded. Therefore, if we can learn to uh, see the pattern in the data, it will be more useful compared to those that we can obtain using attribute data only. Okay. And later on, you will see that using variable measurements, this is the only way to overcome the need for very large and large subgroups. And large subgroups sometimes is a must in a typical attribute control chart. Remember, when the process becomes significantly better, this means the chance to see one problem or one defect is very rare. And this means sometimes we have to inspect the entire batch of production, and that leads to very large subgroup size. Okay. There are three common variable control chart types. So we have X and R, we have X and S, and we have individuals and moving range charts. So what does it mean, X? So as you can see here, each of the type have two components. Okay, the first one have X. The second component of the first type is R. So the first component of the second type is X, and the second type is S. Okay. The third type, the individuals and moving range, this one will be relatively complicated, and it is advisable for you to read on the textbook if you wanted to. You can also see those in the slide, but this one will not be covered in our exam because the calculation involved will be significant. So in this, we will take a look at the two type only, okay? The X bar and R, the X and S. So what does it mean X? Actually, it's supposed to be, it's not just X, but X bar to be correct. So what does it mean X bar? This means average, okay? You guys already know anything with bar is average, okay? Again, the same thing, this is average. R stand for range. You guys already know range, this means the difference between the minimum and the maximum, okay? In a lot of data, the difference between the maximum and the minimum is very useful. But in some cases, for example, in the case of having outliers, so what does it mean outliers? So outliers, this means these data that are extremely different from the rest. For example, let's say we have a bunch of data like this. Okay. So let's say we have 4 points like that. And you know that, the function that we can actually always assume we have a very linear relationship. I don't know why this one is bad. Okay. Let's say we have 4 points like that. Okay. This means we can always find a linear relationship between the two. But sometimes we have some point like this. Okay. And this. So these points are considered to be outliers. And in those cases, the difference between the minimum and the maximum is significantly changed. And therefore, the range chart can be problematic in dealing with those cases. And that is why people involve S chart. Okay, so S stands for standard deviation. So you guys already know the average deviation away from the mean of the sample. So later on, we will take a look at the formula in the control charts. So these are the rules of thumb to apply for these cases. First one, the subgroup size should be large enough, but will not be so large compared to those in attribute control charts. For the individuals and moving range, we only need one variable measurement. Of course, if we only need one, then we need to do a lot more calculation to get more information from the data. So in our course, we will take a look at these two, X bar and R, and X bar and S charts. So for X bar and R, we can use anywhere between 2 to 9. Okay, minimum is 2. So 2 to 9 is a good place to start for the subgroup size for if we use both X chart and R chart. Okay. If we use X chart and S chart, then we need 10 or more per subgroup. So when we have 10 or more, based on the law of large number, the standard deviation will be a significant parameter to estimate the true spread of the distribution. Okay. And that is for the subgroup size. And for the subgroup frequency, so how often should we perform the measurement? It is entirely depending on the nature of the process, as I've said many times. So we have to see where we can find the largest variation, and we supposed to do the inspection in those time in order to actually control the process better. So again, in order to determine the optimal subgroup frequency, we have to consult the R&D or engineering department for the consultation. All right. So just to remember, in this variable control charts, so instead of just one chart, we have two charts. Okay. So that is one of the best benefits. One, we have the average. Here we have the spread. So the difference between the minimum and the maximum. So in order for the process to be stable, both of the chart here and here, X and R, have to be both stable. Okay. And similarly for the second chart, X and S. So for this process to be stable, both of the charts, X chart and S chart, have to be both stable, right? So this means two conditions have to be satisfied at the same time. This means we don't need larger subgroups, and that is the only advantage we can get using a combined charts framework like this. Okay, so instead of having only one chart and having more subgroup size, larger subgroup size, we can have a much smaller subgroup size, but we have to get more data, we get more measurement from those. This means we use two different kind of charts at the same time. So let's take a look at the first examples. So please work along, all right? In this example, we will use X bar and R chart. So the application of interest is a pharmaceutical company. So making drug products. And this pharmaceutical company want to perform a statistical process control on the nominal specs of their vials. Okay, so uh, they need to fill with 52 grams of drugs. So remember, these are pharmaceutical products. So it's really important to get the correct amount or very close to the correct amount. And therefore, they take the measurement really seriously. And every 5 minutes, they take a sample of 6 vials, okay, during a 105-minute period. So in total, how many samples that they have to collect? Anyone? Total, how many samples should we collect? Every 5 minutes, we collect 6 samples. And in 105 minutes, in total, how many samples should we collect? Eh? No answer? What? 126? Okay, how come you get this number? So 21. Okay. 21 times 6. Remember, every 5 minutes, we take one. Okay. So this means there will be 21 interval. All right. 21 intervals, but we have to take 22 times. So that will be 22 times 6, and that is 132 samples. All right. Remember, we have to the interval doesn't count the start and the, if you don't count the start or you don't count the end. So basically we need one more, and that is 22 set of 6 samples each. Okay. So how do we construct the X bar and R chart? So this means we have two charts to work with. The first one will be the X bar chart. As you can see that this is the on the right hand side, you can see the information on the X bar chart. Remember, as I've said, for a process to be stable, both charts have to be stable. Okay? This is the X bar chart, and this is the R chart. So what does it mean, X bar? So X bar, the average process of the X bar, this means X bar is the average on each of the subgroup. All right, so every 5 minutes we have 6 samples. So this means X bar here is supposed to be X bar I. This means the average of 6 samples. Okay, this means we have 22 type 22 X bar. All right. Then we have the grand mean. We call the process average of the X bar chart will be X double bar. So X double bar, 2 dimensions. All right. So that is the sum of all X bar divided by K. K is the number of subgroups. So in this case, K is 22. All right. So K is 22. So we already have the process average for the X bar. And how about the upper and lower control limits? So here we have upper control limits of X bar chart and lower control limits of X bar chart. So here you see this is the process average. So X double bar. So in this case, we don't have 3 sigma, but we have plus and minus A2 times R bar. So what is A2? So A2, in order to find A2, please go forward to the next few slides. You can see A2. Can you see this uh, in this slides? So how can we find A2 in this case? You can see the first column, the number of observation in each subgroup. Okay, and this is N. So how many samples do we have in each subgroup? Remember, we take 6 vials in every 5 minutes. So N is 6. Okay. So we use this row. We need to find A2. So what is A2? So A2 is here, 0.483. Okay. So we use here, I think, okay. So A2 is 0. Oh, I don't know why this is bad in the chart. So A2 will be 0.483. So for the X bar chart, we already have A2. So now our job is to find R bar. So what is R bar? So R bar is basically the same here. So this is R bar. Okay. So R bar is the process also the same like the process average in the R chart. All right. So how do we calculate the R bar? So remember the range, R stands for range. So range is the difference between the maximum value and the minimum value. So in this case, we sum all of the difference between the maximum value and minimum value in each subgroup. And is divided by the total number of subgroup, which is K, which is 22. So we can get R bar and use the information of R bar plug into the equation of X bar. We can calculate the upper control limit for X bar and lower control limit for X bar. And that is the first chart. So we calculate this component, plot the chart. Okay. Determine all of the zone, check is there any violation on any rules. If not, if there is no violation, then we say the X bar process is stable. But in order for the process to be stable, the R chart have to be stable as well. So we need to take a look at the upper and the lower control limits for R, and we do the same thing. However, in the R chart, the upper control limit and lower control limit for R chart depending on two new parameters, that is D4 and D3. Again, D4 and D3 can be found in the same table that we have here. So the number of observation in each subgroup is 6. So this means D3 and D4 will be D3 is 0, D4 is 2.004. Okay, so use these two constant and put in, replace them in the formula here. And we can get the upper control limit for R and lower control limits for R. And we will construct the R chart. Again, split the upper control limit and lower control limit into 6 equal zones, ABC upper, ABC lower, and apply the 7 rules that we had learned before. And for the process to be stable, both of the X bar process and the R process have to be stable. Okay. So far, so good. Do you have any question? No question? All right. So if there's no question, then please work along, because one of your final question will be something like this, or either this X bar and R, or either X bar and S. And it will take a very long time to do this task. So you have to get familiar with the process. Okay, here you see that we have 22 observation. Start at 9:30 and end at 11:15. Okay, so 105 minutes. So here we have six different measurement. Here you see the measurement in grams. So it's not exactly 52 grams, because 52 grams is the nominal value. But in practice, the total field amount actually vary somehow. So you can try to work along. We can, of course, the first one I will help you to. So this is the first group of subgroup measurement. Okay. So you need to construct, you need to find the R, the range. So what is range? The difference between the maximum and the minimum. So what is the maximum in the first subgroup? The maximum is 53.1, okay? And the minimum is 52.22. All right. So the range here is actually this one here will be 53.1 minus 52. Whoa. So R1 is 53.1 minus 52.22. Okay. So in Excel, you can use the formula. Basically, you can use in Excel, there are two commands that you can use. So max something minus mean command. Okay. You can get the maximum in the row and minus the minimum in the row. All right, that is the range. And next one, you have the X bar. So what does it mean, X bar? That is average of the 6 measurement in that subgroups. Okay. So this means we sum all of these 6 number together divided by 6, then you can get X bar. In Excel, you can use average. Okay. So that is the first subgroup measurement. So please try to work along. In your final, it will be something like this. Okay, close to this. We have many observations like this. So it will take a lot of time. Better be prepared. And if you want to use Excel to speed up the process, this is okay. If you want to calculate manually, it's fine too. So please work along. Your job is to construct, your job is to calculate the rest of the subgroups at least halfway, or you can use Excel for the rest, okay? So that you get familiar with the calculation process. Các bạn nào gặp vấn đề về formula trong Excel nói thầy share màn hình cho thầy để thầy chỉ cho các bạn làm ha. All right, any problem for the first calculation of R and X bar? Please show your screen. I can help you. Okay, how is it, everyone? Any issue? So you're supposed to get something. You're supposed to get something like this. Okay. I had shared the Excel worksheet. You can see we have RI. So the maximum minus the minimum, and X bar is just the average, as I mentioned. So put it all together, then you can calculate the X double bar and R bar. So the average of all R, average of all X. Okay. Anyone have problem coming up to those number? Of course, some small difference in the last floating point number is fine. No worry. But any problems? We have already like 40 minutes or so. Remember there will be one question like this, and you are only allowed like maximum 1 hour. And there are some other questions as well. So there will be some questions on identifying the out of control problem. So that will take some time as well. So the total time allowed for the final will be 2 hours. Of course, it will be open book as usual. No, no issue. Anyone try? Remember, if you don't try, there is a big problem in your final. Okay. So be sure to try. Hmm? All right, if no issue, then let's move on. We will continue. Okay, assume we already done all of the calculation for R and X bar. Eventually, you can calculate, as I mentioned here, this is R bar. You can use this is the D3 and D4. So 2.004, you can actually now I use 2. It's fine too. This is 0. So here you can see this is LCL, we have D3. UCL, we have D4. Okay. So this is D3 and this is D4. So here you can see the sample mean plot and this is the sample range plot. So you have to split into 6 equal zone between the upper control limit and lower control limit as usual. So you can calculate 1 sigma. And you can see that there are some points here, 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 here that are falling outside of the upper and lower control limits. All right. So this is for the X bar chart. This is the X bar chart. This is the R chart. So this means, as I've mentioned before, if only even if one chart shows a size of instability, this means the process is unstable, right? Regardless of the next chart. And in order for the process to be stable, both charts have to be stable. For example, now you can see that the R chart is quite stable. So this is stable, but this is not stable. The X chart is not stable. So the whole process is not stable. Okay. So our conclusion is that the process is not stable. All right. Do you have any questions so far? No? Okay. If no issue, then let's move on to another one. So next we have X bar and S charts. Okay. So X bar and S chart, remember these are still two separate charts. And X bar chart, we use the same method of construction like we have before. So this means everything from this we can totally reuse. This means that for the X bar, we need to calculate R bar. Okay. So a good example is actually using the same pharmaceutical data set that we had before and calculate for the new chart, which is the S chart. So the S chart, remember S stands for standard deviation. And standard deviation, the formula is over here. Okay, the standard deviation is basically the sum of x minus x bar square in that line. Okay, for example, if you have 5 value x1, 6 value to x6, okay, and you have x bar here. So this means Si, so will be x1 minus x bar square plus x2 minus x bar square until x6. x6 minus x bar square all divided by 5. Okay. Writing all divided by 5. Okay. Uh, it is important to double check if your calculators has the standard deviation calculation. Make sure that it follows the same because there are two way of calculating. There is one formula. Actually, this is divided by n, which is not correct. Okay, those are only good for variance, and this is standard deviation, which is slightly different. So you have to use n minus 1 in this case. So again, if you have a lot of data, you can do the same thing. So calculate x bar for each subgroup, standard deviation for each subgroup. Okay, and at the end, you still have the same thing. So you have a list of S bar. All right, and how do we construct the rest? So for S, after we calculate the S bar, okay, so S bar will be the sum of all S divided by K, as I had shown here. So for the upper control limits for the S chart, we use B4 constant times S bar. Low control limits is B3 constant times S bar. And where do we find a B3 and B4? Again, in the same table of content, table of all of the constant, basically B3 and B4. So B3 and B4, B3 is 0.03 and B4 is 1.97. All right. So almost a 0 and 2. So you can do exactly the same thing for the other case, similar to uh, the one we already have. So if you wanted to try, please perform the same thing using S chart. Okay. So at the end, so you're supposed to get to the same result because the X bar and the X bar is actually shows the signs of instability. So this means even if we use X bar and S, the process is still not stable and out of control. Okay. So the result will be exactly the same. Even if we use X bar and S chart. Remember the X bar and S chart will be more complicated because we have to calculate if for the X bar, we need to calculate X bar and R bar, all right, and S as well. So 3 more parameters, which is very time consuming. Okay, any questions for the S chart, X bar and S chart, everyone? Mm, no issue? All right. If no issue, then let's move on. So at the end, I will give you one more exercise for you to practice. Okay. So remember in real life, the data are usually multivariate. So what does it mean, multivariate? This means one parameter may depending on many other parameters. Okay. So this means if we use the incorrect, you know, process may be stable with one kind of grouping, but it may be unstable for another grouping. All right. So choosing the what kind of data for analysis is actually important, is relatively important in this case. And therefore, before we actually try to construct the SPC, especially variable control chart, you have to get the in-depth knowledge about the process so that we can know which one is more suitable to be used, X bar, R, or S. Okay. So you can choose X bar and R or X bar and S. It's highly depending on the nature of the process. So uh, so that you know the key variable. Okay, it's important is the key variable that will be the most important to the entire process, and we can just choose any parameter. Okay, so the table of constant actually is useful in many cases. So here you can see in some cases, even when the observation in one subgroup can be very large, and you don't need any constant. You can just use an experimental formula for those constant over here. But most likely you will see the number of observation per subgroup will be less than 10. So you have to choose accordingly. Okay. For example, if the number of observation per subgroup is 4, then you use this, everything in this row. And I highly recommend it for you to print this table in large format so that you can check easily. Okay, remember this one is easy, but you have to be very careful because there are a lot of constant. Have to be sure that you choose the correct one. Okay, so let's take a look at the overall flowchart to recommend the control charts. So when we start, this is the flowchart. So the question will be what kind of data type that we have. All right. So if the data type is more like qualitative, like color or so, we don't have really specific, we can't actually measure properly, or we just want to count the number of time we see something, some kind of events, then it's better to use attribute control charts. So what do we have? We have P, we have NP, we have C, U charts. Okay. All right. So if our data is more like the variables, so this means we can quantify the properties like weight, size, volume, and things like that, then it's better to use variable control charts. Okay. So the next question will be, what is the subgroup size? So if we can only take very limited number of measurement, this means subgroup size is 1. Then it's the only way to use is to use individuals and moving range control charts. Okay. If subgroup size is between 2 and 9 inclusive, then it's better to use X bar and R charts. So if the subgroup size is 10 or more, then it's better to use X bar and S chart. But remember, when you have to use S chart, then you have to also calculate the R chart as well. So basically the X bar and S will be more complicated. And remember, as I have mentioned before, so all these can be programmed into Excel, then you can use them. It's not just for this course, but anything that you want to monitor. So you can use this kind of framework. And the combination of two types actually are very useful in many cases. For example, the process average, the spread of the average, okay, are always a good predictors for many process information. You can also find the summary of some of the common formula. For example, you can see here, you have NP chart, you have P chart, you have C chart, you have U chart. So the average control limits, okay, plus and minus 3 sigma, everything is already here for you to use. And for variable control chart, here you have X bar and range, X bar and S, this is standard deviation, okay? And moving range, this is median and individual moving range. So, but we only focus on the first two, so should be fine. Here, this is the formula for standard deviation. Okay. Do you have any other question for this, everyone? Any problem? If not, then let's move on to another topic. So this is the slide supposed to accompany the lecture note. And in this, we will talk about the something we call the process capability. So what does it mean, process capability? And this is one of the most important parameters because it is broadly defined as the ability of a process to meet the customer expectations. So what does it mean? Even when the process is in control, the question is whether the process is capable of meeting customer specification. That is another story. Okay. And what we already know, for a process to be stable and based on rule number 1, all of the measurements have to be within the upper and lower control limits. Okay, that is rule number 1. Of course, there are some rules that specify, the other rules number 2 to rule number 7 as well. But for customer perspective, customer don't really have the control limits level. But for customer, the customer have something we call the specification limits level. So the level that is acceptable to the customer. Okay, and we have two levels, and that is upper and lower specifications limit, USL and LSL. And these two levels can be completely different from what we can actually do. So I repeat, what we can actually do will be the upper and lower control limits for our process. And what customer want may not be the same. We try to get to as close to the expectation of customer as possible, but sometimes it's not exactly easy. Okay, so this means how can we assure our process capability, and what are the way to quantify those? So let's take a look at this graph. Okay, so we have 4 cases: the one in red, the one in orange, the one in light green, and the one in dark green. So the one in dark green, you can see that we have CP is 2. So CP is process capability coefficient, and you can see that it calculated using upper specification limits minus lower specification limits divided by 6 sigma. All right. And remember, in our control charts, the distance between the upper control limits and low control limit is 6 sigma. All right. So this means This means 6 sigma is actually the distance between the upper control limit and the lower control limits. And in this case, it's exactly symmetrical. So you can see there are maybe we take a look at the two extreme. Okay, the dark green CP is 2 and the red CP is 0.67. So what does it mean? For the case of dark green, all right. So the case of dark green, in order for CP is greater than 1, this means the spread of what we can make, you can see that the dark green case, the distribution is very peaked. All right. So CP is greater than 1. This means distribution is more peaked. Okay. CP less than 1, distribution is more flat. What happened when the distribution is more peaked? Remember from Taguchi loss function, if we deviate away too much from the nominal value, which is the middle value, the higher cost that we are going to have is exactly the same. So if the distribution is more flat, this means the portion of our process that is outside of the control limit, the customer specification limit will be higher. Okay, and you can see in the dark green case, almost nothing outside of the uh, limit proposed by customer. But in the red case, we have a lot that is falling outside of the customer specs. So this means what? This only means one thing. For the case of CB is less than 1, a lot of what we make will not be acceptable by customer standards, right? And in the case of dark green, almost nothing that we make are not good according to the customer standard. This means what we make are in, almost 100% of what we make is high quality. On the contrary, when CP is less than 1, for example, if a CP is 0.67, like the case in red, we may have like 15% rejection rate. So this means we make 100 products, 85 will be accepted by the customer, 15 have to be discarded. They will not receive those. This means the actual product cost, actual unit product cost will be significantly higher in the case of having CP less than 1. Okay, so far so good, everyone. Any issue? All right. So for a process that is symmetrical, okay, this is easy, but things get worse when the process is not symmetrical. So in those two cases, when the process is not symmetrical, for example, the process skew to the left or skew to the right, and we have to use additional process capability coefficients. So instead of just having CP, that is USL minus LSL divided by 6 sigma, we call a two-sided specs. And we have CPL, okay, to the left side, and that is LSL minus the mean, mu is the mean, divided by 3 sigma, okay, if that is to the left. And CPU, that is USL minus mu divided by 3 sigma, okay. And the thing is, for the process that is not symmetrical, so instead of CP, we have to use another parameter that is the CPK, which is the minimum of the two. So CPK will be the minimum of CPL and CPU. So these two parameters, which one is lower, we will get the lower one. Okay, worst case analysis. All right. So we use the worst possible case to indicate the real process capability. And the thing is how to interpret CPK. So if CPK is less than 1, okay, so the process is stable but not capable, okay. And if CPK is 1, this means the process is stable and marginally capable. And CPK greater than 1, this means the process is stable and capable. All right. Remember, in order to calculate the process capability, the process have to be stable first. So here you can see some example of different cases, like CPK, and this is screw to the left, screw to the right. So we have this actually happen a lot in practice. For example, sometimes our machine or the service personnel actually have some problem. For example, like health issue or so, then the process will shift to the right or to the left by some constant. Okay, and you can see in the case of the dark green, remember the original value of CP is 2. So even if the process go to the right and CPK is still 1.5, all right, and that is still very good. However, the other cases, for example, the one in light green, last time we have 1.5, now it's become 0.83. So this means there is some component that is already maybe 1 or 2% that is falling outside of the upper spec limit proposed by customer. So this means the rejection rate starts to increase. And things get really bad for the case of the orange case. CP is 1, but now it's become 0.5 only. And it's really, really bad for the case of the red. Last time, CP is 0.67. Now, shifted 0.5 is actually become 0.17 only. And you can see that 40% of what we make will be rejected, which is a really bad scenario. Okay, so here you can see we have more cases to illustrate the stability and capability of the process. So here you can see the first case, CP is greater than 1. In that case, the first one, the top left, CP is greater than 1.67. CPK is also greater than 1.67. So the process is capable and center. All right. The top right figure, so you can see CPK is less than 1 because the process is falling outside of the lower spec limit. So not capable, not center, and of course not stable. And the bottom left corner figure, so you can see that CPK is less than 1. So this means the process is stable, center, but not capable, right? Because CPK is less than 1. And the bottom right figure, CP is less than 1. So the process is not capable, not center. All right, you can see that we have significantly high rejection rate. So out of the 4 cases, only the top left cases are preferable. And in order to be effective, CP and CPK have to be greater than 1.67, which is a very difficult condition. So here you can see the illustration between CP and CPK. All right. So you can see the top right figure. CP is high, CPK is high as well. So everything is very close to the bull's eyes. All right. So top left figure, CP is low, CPK is low. As you can see, it's spreading all around. And the bottom figure, so CP is high, but CPK is low. So uh, repetitivity, uh, repetition is good, but the precision is not good. So out of these cases, only the CP and CPK is both have to be high for the process to be really good. So in this, you can also see the implications of a Six Sigma process with respect to CP and CPK coefficient. So before that, let me upload this to you first. Okay, so Six Sigma, what does it mean, a Six Sigma process? So Six Sigma is defined that we have 3.4 defects per 1 million opportunities, okay? So this means first pass yield is 99.9997%, all right? Those number actually translated to a CP of 2. So that is why CP of 2 is a proper indicator for a Six Sigma process. And you can see DPMO, so defects per million opportunities is 0.00197. Okay. And when things get really bad, this means the process have been shifted by 1.5 sigma. Okay. So CP of 2 process is still get 1.5 of CPK, and 1.67 still get 1.17 CPK, and a 1.33 CP can still become like 0.83. This means it's slightly not capable. However, when CP is 1, when the process is shifted by 1.5 sigma, then CPKs become very low, become 0.5 only. This means we have 66,000 rejection out of 1 million, about 7%. And if we have CP of 0.67, this means when the process shifted by 1.5 sigma, which is usually happening in practice, then we have 300,000 rejection out of 1 million, and that is extremely bad. Okay. So now you can fully understand the importance of CP and CPK for a process. Our aim is always to target 1.67 or above, 1.67 to 2. And in order to get 2, this means we already achieved the Six Sigma level. Remember, for our control chart, we only have 3 sigma on one side, and this means 6 sigma on one side. Okay, CP is 2, this means 6 sigma on one side. All right, is there any other questions? Hmm? No? Okay, if there's no question, actually I have prepared one exercise for you to try. You can see the additional exercise I posted in the chat right here, or you can see in the slide. You can see in my slide is okay too. So I will share the slide again and try to do it in like 30 minutes or so, because the scale of the problem have been reduced. And in your final, you will have maybe twice as long. So here you have the a bank, all right? So a bank with many operations, okay? So the customer, this is the, some people actually measure the customer service time per employee, okay? And uh, we have taking like uh, 12 days of measurement, and each time we have 5 measurement. So the subgroup size is 5. So the observation time represent the service time per customer. You can see the service time varies significantly. Sometimes we service time per customer is like 1.5 minutes. Sometimes it can be like 8 minutes or so. So it's actually very significantly. So your job is to develop the X chart and R chart to see whether the customer service process at this bank is stable using X bar and R charts. You can calculate manually or you can use Excel. It's up to you. So let's try. Okay. Anyone done? Okay. Done with X bar and R at least. Everyone? No? Where is everyone? Oh my God, I hate online teaching. Hmm. All right, everyone. Ooh, on gone. Okay, so the solution is already provided in the slide, in the chat box. Okay, this is, you can actually do the same if you want. Please go back home and try. All of the, you can see that all six zones with the upper control limit and low control limit for each of the parameters, for example, like x bar and r, we can use that to calculate the sigma for each. And using those, we can actually construct the six zone like we had before. So after constructing the six zone, you can use the same rules, same 7 set of rules to check for violation. So far in this, there is no particular violation for any of the rules. Okay. So the process is stable because both of the chart XB and X bar and R are both stable. All right, any questions, any feedback, everyone? You have any other issue? Do you want to have one more session? No? Okay, if there is no issue, then I think that's it for our control chart. I will prepare one more makeup class I will announce later. So I will try to book a room, but the room is, I will try to book a room, hopefully on, if I can find one room, it will be offline on Saturday as usual. But if not, we will use online, one more online session for you to ask any question. And I will also uh, provide you with the a list of paper for you to read. Oh, okay. There is no uh, group registration form. So I will prepare one for you right now. Okay, please use the link provided here for registration. Fill in the member ID and name. Okay, I will also post the announcement in Blackboard. The deadline for the group submission will be 1 week after the exam. So uh, it's better to focus on your exam so that after the exam you can uh, take a quick look at the all of the papers and generate the summary. I will provide the template question for each of the paper, what kind of information you should get, okay? And prepare the slides and record the video explaining the papers. That's it. Okay. So 3 papers per group. So one group can have five or 6 members. Okay, without any issue. All right. Do you have any other question? If not, we will end our lecture today. I will prepare one more session for those who have any questions. Hopefully, it will be offline. I will ask for permission one more right now. Okay. Hmm. Please watch out for my announcement on Blackboard. For one more makeup class, I will ask for a smaller room this time, very small room, so 50, maximum 50, okay, so that it will be easier to ask for the room. All of the big room have been reserved. last time. So this time we try smaller room. So it will be easier. And okay, if you have any other question, please ask. If not, I will end the lecture right now. So later on, I will also upload this onto something like YouTube or some place. So the student who are not here can rewatch. And watch out for my announcement on one more Q&A, question and answer session on Saturday afternoon, just like our usual uh, class. But the room will be changed. Okay. I cannot book the big room anymore. So the smaller room may be okay. All right. Thank you very much, everyone, and have a nice day. So watch out for my announcement on the Q&A room on Saturday afternoon. And also I will upload the list of paper and will randomize the paper list for you to read based on the feedback on the Google form. Okay. Please watch out for those as well. All right. Goodbye, everyone. I will stop sharing now. Also stop the recording.